So one of the ways we can conceptually understand motion and modeling forces is with free body diagrams, otherwise known as force diagrams. And in this video, I'm going to walk you through a few different scenarios where we would essentially draw a free body diagram to represent the amount of forces that are acting on an object. So you'll notice we have 5 different examples here. I'm going to talk about each of them in detail. Let's start with a physics book lying on a table. So seemingly this physics book isn't really doing anything. We'd think nothing's really going on there. But there are net forces acting on this book. Gravity, since the book is on, in this case, the book is on Earth, gravity is pulling it down. So what is keeping this from falling through the table? So as we represent the textbook just kind of as a dot, because again, we physicists are such good artists. And we draw an arrow pointing down because forces are vectors. So the direction matters. Gravity is always pointed down. We denote down because it's pointing down towards the Earth, right, towards the center of the Earth. And we would represent that as F with a little subscript G denoting that's the gravitational force on the object. But again, if I were just to leave it like this, I would assume that it's just going to keep moving down. So there has to be a counteracting force because the book is still, it's stationary. It's not jumping off the table. It's not falling through. There is an equal and opposite force from the table pushing it up. And we call this the normal force. Well, the term normal in mathematics means perpendicular to a plane. Because the plane of the table is horizontal, it's perpendicular to that. In this case, it's directly opposite gravity. They would be equal in magnitude. If I look at Newton's second law, for the net forces, the way I would look at that. So the force, the net force is the same as summing all the forces together. And this is just the Greek letter sigma. Not to make it scary, it literally just means I'm going to take all the forces, I'm going to add them together. Okay, we're not doing Riemann sums or anything like that for this. This is just as simple as saying, I'm going to take my 2 forces, F, and then I'm going to add it to Fg. And I can account for the direction here in the note, let's call up positive, down negative. So that would be plus a negative Fg or minus Fg. And that's going to equal, by Newton's second law, the mass times the object's acceleration. In this case, the object isn't accelerating. So that is 0. It has mass, but anything times 0 is 0. So I get that the normal force minus the gravitational force is equal to 0. And if I just add gravitational force to both sides of my equation, I get the normal force is equal to the gravitational force. And this is going to be true for even objects that are moving horizontally, so long as they're not moving vertically. So like a car driving on the road, so long as the road is completely horizontal, this is going to be true. The normal force is always going to counteract the gravitational force. And this is how we would represent that and put it into vectors and essentially use mathematics to represent that. Our next example would be a car speeding up. So again, I briefly mentioned, so again, the dot, that's my beautiful car right there, that this car is still technically on Earth and it's horizontal to the plane. So gravity's still pulling the car down, right? So we call this Fg. And the road is pushing the car up, right? The road's keeping the car from falling through the road. So I would call this, again, Fn. And for normal force, the road is perpendicular to the force it pushes is perpendicular to the plane of the road. So it's normal, it's keeping it steady. If the car is accelerating, then that means that it has acceleration force that's pushing it forward. And this is, I would call Fa applied force, particularly for the car. This is going to come from the engine propulsing, can't speak English today, propulsing the wheels forward. The wheels then push on the asphalt and push the car forward. And in actual reality, cars, because tires are made of rubber and asphalt is as such, cars have a decent amount of friction with the road because they spin. So there would be a little bit of friction. You know, really bad at horizontal lines. Little bit of friction. Fk. I'm going to call it Ff. Little subscript F for friction force. K comes from kinetic, which means this is a friction force on a moving object. The object is moving kinetic. Kinetic means to move. This isn't the only thing that would slow down the car, but you're probably somewhat familiar. If I take my foot off the gas pedal, the car would eventually start slowing down. A little bit more to do with that in terms of the car. You got to talk about the axles and the wheels and stuff. But for the case of where the tires meet the road, we can kind of just simplify it as there's a friction force between the tires and the road that's going to slow the car down. And this would be the way I would represent this force. So we can represent the net forces for these. We have to consider two directions in this case. I have net force in the vertical direction. I have net force in the horizontal direction. And I really can't combine these because we've talked about forces are vectors. The direction matters. And if I'm completely in the vertical direction and completely in the horizontal direction, they don't interact. They, in the mathematical term for that, would be orthogonal. Which means that they are perpendicular to each other. There's no interaction between them. So the vertical direction stays kind of independent of the horizontal direction. In this case, then, the net force, I would denote this as having a net force in the y direction. I would just add a little y there. And that's notational preference. You'll see some people write it differently, but this is just to say, what is my net force solely in the vertical direction? And that's going to be the normal force minus the gravitational force, because I'm counting that gravitational is going down. If you wanted to be wacky and weird, you could call down the positive direction and up the negative direction. You can totally do that. Just make sure whatever coordinate system you set up, you stay uniform throughout. But generally, we denote up as positive, down as negative, right as positive, left as negative. And that's going to equal the mass times the acceleration. And this would be just the vertical acceleration. So I'm going to denote a little y there to denote that's just the vertical acceleration. And this is a car driving on the road. It doesn't have vertical acceleration. It's not going up or down, right? The car is not all of a sudden bouncing. That'd be fun to look at free body diagram of one of those, cars that bounce. I'm thinking of the one from the movie Cars, actually. So in this case, that's 0. The normal force is equal to the gravitational force in this case. And that's going to be the same for any object on a horizontal plane that isn't accelerating vertically. It'll change in some of the scenarios we'll look at, you'll see later on. But the net force in the x direction is a different story. Now the formula is the same. I have it as the sum of the forces. Well, all the forces add up in the x direction. Again, we said, let's have y be the positive direction. So this is the positive direction and this is the negative direction. So that would be the applied force, which means essentially the force is coming from the engine, the car revving up. You push your foot to the gas pedal ignites the engine in the car, and it propulses you forward. And then from that, I'm going to subtract the friction force. This is going to come from any object moving across the surface. Part of friction force comes from actually an electromagnetic force, which is one of the 4 fundamental forces of the universe. The fact that the tires are made up of atoms and elements that have electrons. The road is made up of atoms and elements that have electrons, and those brush past each other. There's some resistance with that, which is actually why when you rub your hands together real fast, you create heat. Friction is kind of a way that steals energy from a system and produces it in the form of heat. So this is then going to equal the mass times the horizontal acceleration. And I've drawn this as such because if the car is speeding up, that means it has to have a net force. It means that it is accelerating. It's accelerating in the positive direction. By its definition, acceleration is the change in speed. So if I'm speeding up, I'm increasing in my speed, my acceleration is positive. It's some positive quantity. So my applied force and my kinetic friction force aren't equivalent in this case. I would leave the equation as that. I cannot simplify it unless I know specific variables in that, which case I could solve for one of the unknowns. But that would be how I would represent the car speeding up. Let's look at a car slowing down. Again, so here's my representation of a car. Gravity again, pulling down on it. The normal force again, pushing up on it. We can look at an example later on in the module, in a later module, let's say, of a car going up a hill, where, because in every case, we've been on a horizontal plane, flat surface, right? If a car goes up a hill, if I'm on a slant or an incline, the normal force actually changes a bit, but we will look at that in later modules. So in this case, though, still horizontal plane, I have a normal force pushing directly opposing gravity. If I'm slowing down, the car is now going to experience, so I put my brakes on my car. It has the same frictional force because it's still touching the road, but then it's going to have another force behind it, which we'll call FA, applied force from the brakes of my car. I'm slowing it down, but the brakes slow it down in the opposite direction. Now you'll notice my net force is completely in the negative direction. Now this isn't to say the car's going to immediately start going backwards. In fact, the acceleration takes the speed and starts dropping it down, but it would make my acceleration jump to the negative. So the net force in the y direction is the same. Fn minus Fg is going to equal ma, which is a y, which is 0. Fn is equal to Fg. Then the net force in the x direction in this case is going to equal negative Fk minus Fa. And you'll note, and that's going to equal the mass times the acceleration in the x direction. And everything is negative. I'm going backwards. I'm slowing down, right? And eventually, in the case for this, the way brakes work, the way friction works, I'm not going to slow down infinitely and start going in reverse, right? I'd have to put my car in a gear and shift and go in reverse. So this will just slow down until the car stops is the way that this force is going to work. That's how I would represent a car slowing down. We've particularly looked at net forces in the vertical direction with changing horizontal direction forces. Let's look at what happens if I have changing vertical direction forces. So this is the Blue Ghost lander. It's one of SpaceX's landers on the moon. So this would be an example of Blue Ghost descending on the moon at a constant speed. And the reason I pose the moon example, I'll compare it with the Earth example in a second, but is the moon has no atmosphere. And atmosphere directly denotes drag, right? So atmosphere is essentially made up of a bunch of gaseous particles, 80% nitrogen, about 18% oxygen, and 2% some other miscellaneous gases. And if I'm pushing through those, I mean, essentially those particles, those are substances and elements. As I'm pushing through them, I get resistance. So the faster I go through something, the more resistance I'm going to get, which is why if you've ever stuck your head out the window of a car and it's moving fast, you get a lot of force, a lot of pressure. That's drag. Just by essentially, you can think of it as you're moving through a fluid is really kind of how we mathematically represent that. But on the moon, there's no atmosphere. There's no fluid. So this ghost lander, if it's moving at a constant speed, that tells me my speed's not changing. So dv dt is equal to 0, which means my acceleration is equal to 0. That's what I denote from that, or deduce. Sorry, that's what I deduce from that. So I would represent, again, my beautiful ghost lander. No one's ever drawn it so good. It's going to be pulled down from gravity from the moon. I would still write this as Fg. I don't necessarily need to denote that this is the moon's gravity unless the problem really dictated. That's kind of up to you. But Fg, this is still gravitational force. It's a different type of gravitational force because the moon is about a fourth the mass of Earth, but it's still a gravitational force, right? The moon still gravitationally attracts objects, which is why asteroids hit it. And then I would have in this case, a complete equal force, and I'm going to call it applied force, counteracting gravitational force. This would have to be from the thrusters, which you can kind of see in the image right there. The thrusters from the lander slowing it down so it doesn't crash into the moon. And we can kind of get why that would be appropriate, right? If I didn't let any thrusters on it, I just targeted it at the moon, you can tell they'd just keep going. And they'd speed up, and then eventually they'd crash. And the reason they would crash has to do with impulse, which is a more relation of Newton's second law, which we will explain further in future modules. But essentially, this is how I would represent the free body diagram for this. Now, there are no x-directed forces in this object. I mean, unless he was coming in at an angle. I'm not going to get that complicated for this. We're assuming let's assume he's coming straight down, which would be the optimal way to come down. And we would essentially have no x-directed forces. Everything is the vertical. I can just call it F net. I could specify that it's y direction, or I could just call it F net is equal to the applied force from the thrusters minus the gravitational force. And if, again, constant speed, it's the mass of the lander times the acceleration, which is 0, the thrusters have to completely counteract gravity. And that's a thing we can calculate. We know the acceleration due to the moon's gravity. We can find that later. We'll explain it in the next video you guys will watch for this section on types of forces when we learn about Newton's gravitational force equation. But we can actually calculate, and this is how scientists and astronauts, they calculate these things. How much force do I need to land safely? And sometimes they get it wrong, which is why history has had failed missions, right? But with a lot of practice, a lot of work, they can refine them, make them better, and get them accurate. So that would be an example of this. If I'm going to, before we move on to the next one, I'm going to change this. Let's say the blue ghost lander is descending and accelerating, right? Maybe say it's initially coming close to the moon, it's going kind of fast before it starts slowing down, so that they would be accelerating. Then the only thing I would really change for this is that if it were accelerating, my thrust force, oh, hang on, that should be attached with it. My thrust force would be something less than the gravitational force in that case, in which case they wouldn't equal each other. I would have to represent that. It would have acceleration. We would have acceleration if we did that in this case, you know, we would notice. So the same equation is set up. I just no longer set it equal to 0. I would have essentially these net forces going to equal whatever acceleration they would be. I could actually solve for the acceleration by dividing mass from both sides of the equation. I get A is equal to the applied force minus the gravitational force over the mass. Well, if this is bigger, so the gravitational force is bigger than the thrust force, which we can see it would have to be, we know that this is going to overall be negative, which means the acceleration is going to be negative, which makes sense. If it's accelerating in downwards, I'd see that in negative acceleration, which is where the math takes account for direction and magnitude in that case. Okay, the last example we're going to look at is another SpaceX, but this would be like a rocket, so one of Starlink's. So there's, I want to say there's over like 3,000 Starlink satellites in the atmosphere. They launch them a lot, but essentially they have launches down, I can't remember exactly where in Texas, but they have launches fairly often down in Texas. This is one of their more recent launches. And we're just going to talk about the nature or the free body diagram of a rocket needing to get out of Earth's atmosphere. It actually has to get out of what's called the escape velocity. And where that comes from is not only does it have to escape Earth's gravity, it has to escape Earth's atmosphere. So you guys don't know too much about the drag equation yet. We'll look at that again in the next video. But drag, I want you to think about it. If I'm walking down the street, I'm walking through the atmosphere. I can breathe the air. I'm not really feeling a huge amount of wind or force on me. Now, you can relate that to driving in the car and sticking your head out the window if you were on the freeway. It almost pushes you back, right? There's a lot of force. So there's a relationship with drag that has to do with it increases in resistance force the faster I go. And that just has to do with the fact that you're traveling through particles quicker. But we would draw, so if the SpaceX rocket has to escape Earth's gravity, it has to reach what's called terminal velocity. It has to accelerate to get fast enough to get to that point. Once it leaves a certain amount of atmosphere, it doesn't necessarily actually have to travel at an accelerated rate. It can travel fairly constant at that point. Once the atmosphere density decreases, it's not going to get as much of a decrease in terms of gravitational force from Earth until it's quite a bit away. But it starts changing. And again, these are kind of simplifications of that. But this would be the rocket. Gravity's still pulling down on it, and that's the same. That is literally and we haven't actually explicitly stated this, but if by Newton's second law is the force is equal to the mass times the acceleration. Well, Fg is the gravitational force because of Earth. That's equal to the mass of the object. The acceleration, if it's just specifically the gravitational force, always has to do with the acceleration of Earth's gravity, which we can calculate using another Newton equation. But this is 9.81 meters per second squared, which you might have seen or heard or have been somewhat familiar with. The moon has its own gravitational constant. A whole bunch of other planets do. In fact, there's a list and tables of them, which we will look at some point. But for now, that's pretty consistent. The rocket, and actually, if we wanted to get technical, the rocket's mass does change over time. It burns fuel. As it burns fuel, it gets lighter. But we're, again, going to simplify it. The rocket in general, its mass isn't really going to change much. And gravity, Earth, it's still escaping Earth. So that's pretty consistent as to what it is. It has to have thrusters that are producing more force. We'll call it A for applied force from the thrusters of the rocket to get out of Earth. And in this case, I would say that the net force is going to equal Fa minus Fg, and that's the mass times the rocket's acceleration. It has to accelerate to get out. So the applied force has to be greater than the gravitational force in order for it to leave, in order for it even just to reach escape velocity. And you can think of that as it starts at 0 at the ground. It has to get moving. It has to have enough force, which is why rockets are so expensive. But hopefully that helps you break down a little bit in terms of how we mathematically represent these using free body diagrams, which are just fancy term for vectors of an object to kind of account and assess the forces acting on it.